to one-sided crooked network. So let's call it quits because I had it an hour.
Hello, Rail. Integrable.
你们考试考完了，其他的成绩 OK 吗？还没有出，都没有出。 Hello. Okay. Let's start. Let's not wait. Let's recall what we have learned last week about it. If the upper integral is equal to the lower integral, and then we will call this the integral from, let's say, a to b, integrate from a to b of. Okay, so this bounded doesn't refer to the boundedness here, but then if we have a function defined on the closed bounded interval, right? What's the way to make this function bounded? What property can make a function bounded on a bounded interval? What function, what kind of function you could take? I think there are two kind of function you learn, right? Continuous and differentiable, right? Okay, so you need a continuous function. You can have a continuous function on a closed bounded interval, then you will achieve your maximum and minimum. Okay, so that your function is bounded. Right, this is one way to do it. Although a bounded function might not be continuous, right? So meaning continuous function on a closed bounded interval is always integrable. Okay. So how do we define this upper integral and lower integral, UF and LF? Okay, so UF is taken to be the inf of soup. Inf, okay, inf of some soup, right? Yes, soup of your x such that your x is in. So let me see how I rephrase this. So actually, it's a sum fx time I minus 1 I in some index set. Let's call it P, depend on your partition, right? Okay. Across all the different partition. Does this make sense? Make sense? You look at all the partition, and then you consider the UFP. And you look for the infimum, then you get the upper integral. Okay, similar for your lower integral, it is the soup of the LFP. So LFP, how is it defined? So you get your index set for your partition. It's just this line. Okay. Then inf of fx such that, oh, I didn't tell you what's this x have to pick from, right? So this x pick from xi, that's 1 to xi. Yeah, it's similar. Yeah, I abuse notation a bit, but then I hope you understand what I'm trying to say. Okay. Okay, so far so good. Okay, so trying to tell you that there are some in and soup idea we are looking for. Okay, so maybe we start with a non-example. Last time I think we discussed that this function is not integrable. So this is a Dirichlet function. That fx equals to 1, 0 if x is rational, if x is irrational for the other case. Okay. This is not integrable. Okay, so if you graph this, the 1 and 0 is like scattering around this R2 plane here. So, for example, right, I have 0, 1, 2, 3, 4. All these you get 0. And also for those fraction, you also get 0. But then we learned that irrational number is dense, right? I mean, both of them are dense. So you also find 1 in the between of every 2 0. So actually both above and below, right, almost form a line. I mean, 2 lines inside your graph here. They almost form 2 lines. Almost. Okay. No intersection, but if you look from far, it's like almost 2 lines. Okay, if you look closely, this line here should lie in between 2, 0. Okay, so maybe you can ask yourself, does the area of the under the graph exist or not? Okay, so we will use the definition of integrable to show that this is not integrable. So what do we need to do? Okay, we need to look for any partition, and then compute what's this set here. Okay, this set of number here, and then find out the increment for your upper integral. Similar for your lower integral, you find out this set of numbers here. Okay, and then you compute the soup. Okay, so if you happen to break your, okay, so we just care about 0 to 1, right? Okay, although we could extend this definition here. So we only look for this section here. Okay, so if you have any partition, right, any interval, right, because the rational and irrational are dense, you will always find some rational or irrational inside the interval. Okay, so what does that mean here? Okay, what does that mean? So if you have any partition, okay, just write down any partition. Don't really care how do you partition it. Okay, then for every I in 1, 2 up to n, we actually have the infimum of x for x in ti minus 1 to ti should be 0, and the soup, okay, there's really one choice there, okay, is 1. Okay, so what do you get is the coefficient here. Okay, the coefficient here is always 1 times the length of your subinterval. And then the other coefficient is even easier, it's just 0. So 0 plus 0 is always 0. So this set here is always 0. Soup of 0 is just 0. Okay, but then here, 1 times the length of the subinterval. Okay, so you retain the length of the subinterval, but then what's your total length of your subinterval? You just care from the interval from 0 to 1. So they will always add up to 1. Okay, so in this case here, LFP is always 0. Okay, maybe you can think of it as 0 times x t0 minus, t1 minus t0, and then blah, 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 up to 0 plus, 0 times tn minus 1, right? But then UFP, UFP will be 1 because it is 1 plus 1 times t1 minus t0 plus up to 1 time tn minus 1, right? Okay. But then this would add up to 1 because it's the length of your interval. Does it make sense? Okay. Okay. Yeah. Okay. But then P is arbitrary, right? So meaning you put whatever P in, you just get these two numbers. Yeah, so LF is just the sup of the set containing 0, which is 0, and UF is just inf of the set containing 1, which is 1. Okay, so thus LF is not equals to UF. Okay, hence F is not integrable. Okay. Good. Any question? Okay, no question, then we'll continue. So then we will give another equivalent condition on integrable. So let's name this theorem. So we'll discuss integral analytically. So meaning we'll involve epsilon again. Okay, so in this class, we like epsilon a lot. So again, let our function be bounded, because when we discuss integrability on bounded function, then f is integrable. Okay, meaning the upper integral and the lower integral coincide. If and only if for every epsilon greater than 0, okay, there exists a partition. So now we upgrade our mathematic toys. Okay, so we look at partition that depend on this epsilon, such that we can make our UFP and LFP as close as possible. Okay, so previously I tell you need to be equal, right? So now we change this equal sign to saying that the difference, I can make it as small as possible. As small as possible. There is a partition that help me to do that. Okay. Okay, so previously we was using the inf and sup, okay, to converge to each other. Okay, but now we just use a single p epsilon, okay, that make these two as close as possible. Okay, we use a single p epsilon. So what do you think? Which direction is easier to prove? Which direction is easier? Right to left or left to right? Which one is easier? Usually this kind of statement, there's one side is easier one. Okay, so you need to learn and see which side is easier. Jingwei, you try and give one answer. Guess, conjecture. So first thing you need to learn in mathematics is to make conjecture, to train your intuition. Conjecture. You need to make a conjecture and then verify yourself this thing is correct or wrong. Okay, time's up. Give answer. Conjecture. Exam also like that. You need to write down the solution. Correct or wrong. Conjecture. Then we verify together. 不会。我操，这个就完蛋了。Left to right, right to left 哦 can make choice or not？ 做一个决定，要有决定。选一个也可以，然后我再跟你讲为什么这个东西这个难。但是你一定要做决定先。Right to left 啊 ？Yes, it is right to left. Okay, so we see why is it easier. Okay, so let's see why right to left is easier. So right to left means what? You assume that for every epsilon you can find this p epsilon. Okay, then you need to show me that UFP equals to UF equal to LF. Okay, right. So if you want to show that two things is the same, right? There's one way to show two things is the same, right? Okay, maybe I need to tell this thing to you. Okay. Do you know a lemma or not? A equals to B if and only if for every epsilon greater than 0. The absolute value of A minus B is less than epsilon. Everything, huh? Is this correct? I guess we need them to be, I need them to be positive. Them to be positive. Oh, no need. No need. Yes, no need. I think we did it before, right? We did it before. Huh? Lecture 7. Okay, good. Yeah, we did this before. Everyone can get the idea of this lemma. If there is a positive number, there's always less than, if there's a non-negative number that's less than every positive number, what this number has to be? 0. So in real number, what's the number that have length 0? Only 0. So A minus B have to be 0. Okay. If A equals to B, A minus B is 0, so 0 is less than every epsilon. Very good. Okay, so two direction here. Actually, if and only if. Okay, so we're gonna use this. So let epsilon greater than 0. Then we simply choose P epsilon such that U F P epsilon minus LF P epsilon that is less than 0 epsilon. Okay. So then we do this lemma trick. So to get this right, to get this left-hand side here, I need to do this right-hand side. Okay, so that's why I pick a epsilon here. Okay, so we compute what is the difference between UF and LF. Okay, and we know that this difference here should be greater or equal to 0, right? Last time we showed that UF is always greater or equal to LF. Okay, so I can throw away the absolute value. Okay, but then this UF and LF, right? Remember how we construct them using infimum and supremum, right? Of UFP and LFP, okay, respectively. So I can realize them using the P epsilon. Okay, I mean not realizing, but then compare them to one fixed P epsilon here. Okay, because UF is the inf, right? So UFP should be greater or equals to UF, and then LF is the sup, right? So it should be having the other direction. But then we can make sure that this thing is less than epsilon. Okay, so we reach the right hand side of this condition of this lemma here. Is that okay? Okay, ma'am. Question. Jingwei. Okay, ma'am. You can ask. Good. Okay. So I would say this side is easier because it's just involving the stuff from real number that you need to know about real number here. Okay. The other side is harder. Why is it harder? Because from UF equals to LF, you need to create a P epsilon for every epsilon. Okay, you need to create this P epsilon. Okay, so that's why I say this is harder. Okay. So let's see how we do this side here. It is harder, but not too hard, okay, based on what we have known. So for this direction, we'll assume f is integrable first. Okay, so that is LF equals to UFP. Okay, so what do you want to show? Okay, we want to show that there exists a P epsilon such that UFP epsilon minus LFP epsilon less than epsilon. Okay, for all epsilon values. Well, where can we get the P epsilon? Where can we get P epsilon here? Well, we know that F is integrable, right? So LF and UF exist. So maybe you can play around with LF and UF first. So by the definition of LF and UF. So let's fix an epsilon first. Now fix. We can find actually P epsilon over 2 and P epsilon over 2 for the different two UF and LF such that LFPA epsilon over 2 greater than LF minus epsilon over 2 and UFPB over 2 less than UF plus epsilon. Okay, so there are a few things to see here. So what are the property I'm using here about LF and UF? Remember, the sup and inf, right? Okay, the sup and inf property. And then I choose epsilon over 2 over epsilon, right? So what can you guess here? Why do I choose epsilon over 2? Later, I'm gonna add two things together, okay? So later, I'm gonna add two things together. So I renamed this one is A, one is B, right? So this is obvious, right? I just labeled it depend on the L or U are using. So I'm gonna put these two things together. So I consider UF PB epsilon over 2 and LF PA epsilon over 2. Okay, so what you see here is actually I try to reach this calculation here. Although not quite, because here I need the same partition. But here these two partition might be different. They might be different. Okay, so let's see how can I play around with it. Okay, so I indeed get something less than epsilon, but then it's not good yet, right? Because my P epsilon might be different. These two might be different. So what can we do here? What do you think? Huh? Union. So union means what? I'm taking what's the technical term we learned last week? What's the technical term we learned last week? You create more sub-interval. So you are doing refinement. Okay, so you consider the refinement. So now, since these two partition might not be the same, right? It's not the same. Not necessarily, huh? A is not equal, so not always. How should I say? Not equal always, something like that. Okay. So we look for the refinement. Okay, refinement. So let's see how refinement can help us. So refinement is P epsilon over 2A union with P epsilon 2 over B. So how does refinement could help us? So remember, when we take refinement, our UFP will always decrease. Okay. And then our ULFP will always increase. Okay. So that we get this inequality. Okay, then we know that this thing is bounded above by epsilon. Then we are done. Okay, so when you do refinement, your UFP will decrease. Okay, less than or equal to, and then your LFP will increase. So you are taking away more things. So this difference here becomes smaller. Okay. So question? Question? Feel free to ask. Don't be shy. Yeah. No question? Okay. Yeah, Jingwei, what do you think? Yeah, I need to repeat. No? Okay. Can rewrite or not if I erase everything? This is what I mean by okay. You need to be able to reproduce my proof without looking at the proof. Huh? 反正他也是要从这个。好嘞，so OK，怎么听不到？他讲吗？应该可以，OK，没有应该要可以，他有信心，你应该可以，到考试就变不可以了，要可以，恐分100%。我跟你讲的东西是100%的，所以你输出要100%。OK 吗？有问题尽量问啊，不要拍谁啊。嗯，你考试就问不到了。OK，所以你觉得我讲的容易跟难的点在哪里？Sometimes this is perspective lah, but then sometimes you need to learn about people's perspective. Maybe it's not your perspective, but then that's why you come and learn in school, right? Hey, why we force you learn bio, learn chemistry, learn maths, right? Because you are trying to look at different perspective about this world. Okay. Otherwise, you don't need to come in school. You just learn your own perspective, homeschooling, right? You get the point. Why is it hard? Why is it easy? Mm. No right or wrong answer. You can just answer. Hong Jing can help him or not? Why I say one easy, one hard? Hmm. Okay, so one we just use the real number property. Okay, real number property is like way before integration. But then the other we need to use the integration property about refinement. So it's new stuff. Okay, or not? Does it make sense? So the previous one, I don't need to even know what is integration. Maybe I can do already. Maybe I can give to the midterm question also can. First half, I can give to midterm question, can prove already. But then the second half, we really need to establish some property of refinement first. Only then we can prove this. So that's why I said this is hard. Okay, because it's a new stuff. Okay, does it make sense? Okay. 洪金懂我哋做乜 Okay. 經緯 Okay. Okay. We can because we learn limit language, right? So we can rephrase this language into limit. So there's a corollary. Actually bears a name called the Archimedes-Riemann theorem. I'm not sure why these two guys were matched together. I think they live in a different area. Maybe someone interested can try and find this. I don't know why they are put together. So a function is integrable if and only, if only if there exists a sequence of Pn, a partition of AB such that when you take limit n to infinity, UFPN minus LFPN should be 0. Okay, so this proof is just a limit proof. You can try and reproduce yourself. Okay, a limit proof. Okay, this is just trying to yeah, change this epsilon p to a epsilon n argument. It's like what we did last time. Okay. Okay. So let me see. So this thing will come in handy. Whereby we also have this lemma. So if you have the above property here, UFPN minus LFPN equals 0, actually, you can show that this implies that the limit of UFPN have to be equals to the limit of LFPN. Okay, so well, this is obvious if UFPN and LFPN converges, right? Then you can use limit law. Okay. Yeah, if that converges, then this is just limit law. They necessarily converge. Is the previous same condition from the previous corollary, just a partition of AB. Yeah. If this two sequence exists, right? I mean like converges, right? Then this is just a limit law. So I guess this side to this side is limit law, right? Let's say these two exist, but then from here to here, from left to right, is some easy exercise actually. Okay. Yeah. So let me comment a bit on this proof. So from right to left is just limit law. From left to right, it's not too hard. It's just a limit exercise. So you just write down what does this means, and then try to establish this. Their limit is the same. Actually, maybe hint here is you can use squeeze theorem. Okay. Okay. So why do we do this? So why do we do this is there's a theorem called the common limit criterion. First is if f is integrable, maybe. So let's say you know that it is integrable already, then you can find a sequence of partition maybe such that the limit of LFP, you will reach your LP, okay, sorry, not LP, LF, which is the integral, and the limit of your UFP also will reach your integral, okay, which is UF. Okay, UF and LF is the same if it's integrable. So if you know that it's integrable, then you can find this sequence. And how about the converse? How about the converse? The converse is very strong. If there exists a sequence, the sequence Pn partition of AB, right, such that the two limit coincide, then f is integrable. And at the same time, these two limit is our integral. Okay. So from this limit criteria, right, what do you see is if I can find, okay, a sequence of partitions such that the limit of LFPN is equal to the limit of UFPN, then we know that f is integrable. And then the integral is the two limit here. So now we turn the question of finding infimum and supremum into a sequence. Do you think that this make life easier? Do you think that this make life a bit easier? Because the sequence, right, you just consider Pn, right? Okay, just countable things, right? But then if you look for the infimum and supremum, right, what do you look for? You look for all arbitrary partition. Okay, all arbitrary partition, but then your number is uncountable. That's like uncountable thing you can put in there. Okay, does it make sense? Okay, so this should remind you about your calculus one, your Riemann sum. Why you just divide by n and then your n gets small and then you can show integrability already. Okay, you just look at sequence of partition. Okay. Okay, can appreciate this theorem here. No, no. Okay, so in terms of looking at the set of all partition, we just look at a sequence of partition only. Okay, let's see. Which one you are interested? Do you want to prove A or do you want to prove B? Which one is more interested? More interesting. You want to choose A or B first? How about one way, one way? Is A, B, B? Okay, good. Okay, let's do B. So assume that you have this sequence already, okay, and then you also know that this two limit coincide. We want to show that f is integrable. So we want to show that f is integrable, meaning what? We need to show that LF equals to UF. Okay, we need to show LF equals to UF. Right. So what should we do here? Well, here we are dealing with this LFPN and UFPN, right? So just now at the start of the class, right, we relate these LFPN, UFPN to UFLF by using this. Okay. Okay, so we're gonna prove using this theorem here. Okay, so to talk about UF equals to LF, we can talk about this UFP and LFP. Okay, so we're gonna do this. Okay, so for all epsilon greater than 0, we need to find this P epsilon. Okay, so we're gonna show using this theorem here. Okay, so what should we do? Okay, so let's start. We will show f is integrable by showing for all epsilon greater than 0, there is a p epsilon such that UF p epsilon minus LF p epsilon is less than epsilon. Good. So what's our condition? We have this lim of LFPN and a sup of LFPN here. So this is one place we can apply our epsilon thing, right? So suppose lim of LFPN equals to the lim of UFPN. And then let's call this name L. No, I, maybe. Let's call them I. So for fixed and epsilon greater than 0, then there exists a P, let's call it P also A lah. PA of epsilon over 2 and PB of epsilon over 2 of AB. Such that these two things hold. Okay, so these two things hold. I'm not using supremum or infimum. I'm using one-sided limit. Okay, I'm using one side of the limit. Okay. Actually, you have two sides, but then I just need one side. Does it make sense? Okay, I just use one side of the limit. Okay. Do I need to write in full or you are okay? You're okay with this? Because your limit converge, right? You can write your UF E be epsilon over 2 minus I less than epsilon. I just use one side of it. Then what do we do? Then what do we do? What do we need? We need a P epsilon, right? So now you got two different P, but then I need a single P. Again, we play the same game. We play the same game. What game we play? So we play the refinement game. So let P epsilon to be the union of these two. Then UF P epsilon minus LF P epsilon should be less than or equals to UF P A of B epsilon over 2 minus L of F of PA epsilon over 2. Okay. This is due to the refinement property. And then this is less than I plus epsilon over 2 minus I minus epsilon over 2. Altogether we get. Okay. Good. So we just use refinement property, we just use limit conversion property, then we can prove this integral property. Okay. Anyway, have any question? No? Okay. Can follow. Okay. So the next part then, what do we need to show? We need to show that UF equals to LF equal to this two limit. And since this is integrable, okay, so since we prove that F is integrable, so what does this mean here? This means here, this integral here exists, and it is equal to UF equals to LF. Okay, so this thing here exists. But then we need to show that this number we can get from the limit. Okay, how do we show that this number we can get from the limit? Well, note that we established some inequality last time, right? We can always bound this two term, right, in between some fixed UFP. Okay. In fact, we can fit it in between all the UFP and LFP. But then we know that these two things has limit, right? Limit exists, right? So you squeeze by two sequence that have the same limit. So what does this mean? This means that by squeeze theorem, okay, by squeeze theorem, these two have to be the same, and it is equal to the limit on the left hand side and the right hand side, which is the limit of UFPN and the limit of LFPN. Okay, so this is how you use the squeeze theorem. Okay, does that make sense? Make sense? Okay. Okay, cool. What time? Okay, 10:50. Okay, any question? Any question before we take a break? Okay, if no question, we will show the next example using this kind of calculation. Okay, how this theorem can help us to find the integral, okay, of the function, right, using a partition. Okay, let's take a break and then I will open up the attendance. Hey, why Ping Jie is not here? Where's Ping Jie? What Jie? Oh, 你要 message 啊？哦，你才有问题，你要不要 message 他？ 要找插头，去一个吧，那边 maybe 这边多一个。诶，好像我上不到网，你们上得到网吗？嗯，我上不到啊。再来，OK OK，他忘记课是在哪里？OK，下个礼拜五讲诶，就到那边。诶，我记得我是在他们第一堂要走之前，跟第二场全部人来的时候讲，还没来。哦，我没有重新讲啊，把人然后什么事啊？啊，对对对对对对对，因为我觉得我在班上提了就不提。嗯，谁考完数学？哦，高考啊。嗯，对。哦，你们认识邓紫棋吗？对，他拜六，哎，拜六还是礼拜，在这边开演唱会。不认识啊，不认识邓紫棋啊，我没有去看。我的呢？啊，对，哦，你们的偶像是蔡徐坤的，蔡徐坤对我来说是小孩子。反正邓紫棋讲一个很有逻辑的话，不知道你们看得出吗？我播给你们看。嗯，actually also work as a reminder to most of you 啦。I think 很多数学系的人都是很完美主义的。对，
就是因为你知道原来坏的人他是破费的。当你发现这种的时候，你才会发现原来人生有更美好的事情，不是你要做的很厉害、很完美，不要说很光鲜亮丽，而是你有没有跟你身边的人躺在一状态。
我听得懂他的逻辑啊，听得懂他的逻辑啊，有听到吗？你需要 MA 不是 apply 一下，有没有听懂他的逻辑？It's OK，我先教你听逻辑，这个是一个点哦，就是你不懂那个 definition，不是你要懂它的逻辑在哪里，它的脸，因为有时候我们读 paper 啊，你是不懂 definition 是什么，或者你还没有很明白 definition，but then 你已经要知道那个 paper 在要讲什么东西啊，这些东西要讲 link 在一起。OK，有吗？有人 get 到吗？他讲的逻辑吗？ 有没有 get 到？再播一次啊，试一下这个是 MAT 啊，写 if then 出来啊，你会写什么东西出来？好，你写 if 什么 then 什么啊，什么是 necessary condition，什么是sufficient condition，听一下他讲话是有逻辑的，我等一下跟你解释我怎样理解他的逻辑。
如果完美是存在的话，就不需要有爱了。我再说一遍，如果完美存在的话，就不需要有爱。因为谁都可以喜欢完美的人，但是爱是很种爱，爱是需要包容的。就是因为你知道，原来你爱的人他是破碎的，你自己也是破碎的，他们爱你，他们也要包容。当你发现这种的时候，你才会发现原来人生有更美好的事情，不是只是你要做的很厉害、很完美，你要活得很光鲜亮丽，而是你有没有跟你身边的人产生一份爱。
OK，有吗？if 什么 then 什么？啊，他讲的东西把人最 main 的第一个他讲什么？if perfectionism exists or perfection exists, then 你可以讲 love is not necessary，或者 love doesn't exist 啊，不需要爱 ，right？然后他讲 argue 这个 point，他讲 argue 这个 point，你知道吗？对，没有错。他 contrapositive 是什么？爱是拿来做么？他讲啊，他讲爱是什么？爱是拿来包容啊，爱是 for 破碎的人呢，说爱是 for 不 perfection 的东西。OK，就算你不懂什么是完美，不懂是什么啊，but then 你就知道它的 negation 就懂。OK，right，破碎你可以理解成是perfect 的 negation of perfection。OK，yeah。
也不能这么讲，perfection exists 啊
perfection exists。吗？
可以 approve of people that practice perfectionism people practice non-perfectionism and look for non-perfectionism, not perfectionism. I cannot disprove that the perfectionism, the group of people that practice perfectionism exists. 你讲话有点太。
说有吗？有人要回应吗？七样的，你要回应啊？还是你们懂七样在讲什么？没有听，七样人家没有听你讲的话，你看你讲话都没有用啊，没有人听啊。你讲一点，人家听得懂啊，快点，有听，是不是？你看，没有爱，没有爱啊！我没有要讲那个东西啊，那个对对，不有关系，对。
那你就是完美。那什么是完美存在？来，这是它的 definition。OK，那你写完所有那个 statement 出来，你用 PQRSTUD 会
没有，我觉得现在问题是我们没有在解决你的问题，然后你没有在理解我们的问题，对吧？没有非啊，你不用懂完美的情况下，你就懂他在讲什么了。我们写出来，我们已经写出来了。
他并没有称为完美存在。
完美存在，完美存在这个没事。
这世界上有没有？认为，你知道认为，就是说我们可以完美存在的同时有爱。
哦，是，I think 我觉得这个可以，我觉得这个可以存在，只是我教你理解它的逻辑吧。我觉得你不要理解，你都没有开始理解，你居然理解不到。 你要理解的话，你都不是这样回答，你要去一直问他到底在讲什么，而不是一直讲你要讲的东西嘛。嗯，写啊，写啊，你回去写啊，我都讲出来了。没有啦，I mean like 我们不是讲出来没？全部人都在听啊，听不懂。OK，好，听不懂，听不懂哦，我已经解释了哦，就这样哦，听不懂哦。好，OK，好，好。So 就是那个if perfectionism exists, then love doesn't exist. Yeah, yeah，可以这样。对，不是，他不是讲这个，他只是说 for broken，他没有讲他不 practice perfectionism，but then for broken。OK，我也不会讲 perfectionism 嘛，我就应该讲 perfection。其实 perfectionism 跟 perfection 又有差别，对不对？perfectionism 只是说我要完美，他做的是不是完美我也不知道，他只是要完美吧，一直要完美。perfection 是真的就是完美啊，那个东西就是全部人 agree 都完美，还是不完美的。for OK，我觉得可以讲 for 不完美的人，for 破碎的人，对他这种完美就不存在哦，他的 argument 哦，他 argue 了，他 argue 了 ，contrapositive。对，exist 啊，对，我不 care 那个啊，我只是讲，我没有 proof，我是讲我理解他在讲什么，我没有在 proof 他讲什么，我在理解他在这 argument，我没有在 proof，我没有 proof 给你看。你看你的理解以为在 proof，我没有在 proof。你看我没有在 proof，我只是讲他的逻辑有在那边，我没有去 verify 他的逻辑，把他逻辑在，就是 contrapositive 在 contrapositive，但是 contrapositive 的那个 statement 是 true or false，我不知道。对，没有错，logical，对，没有错，对啊，axiom 没有证明啊，没有证明。没有证明，他是用他的一套 axiom，他的一套，对，就这样哦。我不知道，我真的不知道，我不用知道，我只是在讲他的 axiom，他是有逻辑的。像 axiom real number axiom 这么有逻辑，我不知道这么有逻辑哦，只是它刚好可以用哦。对啊，所以 logical 的东西可能可以没有用，对啊。你 double standard 啊，我先跟你讲啊，你 double standard，你回去想一下，你很常 double standard，我跟你讲。呀，上课要上课。觉得最应该讨论的是为什么还要穿这个货？最后突然间这个重要问题，问题是我们就是讲他讲话有逻辑啊，有逻辑不代表有逻辑的东西不一定对啊。对啊，但是问题是你讲有逻辑代表逻辑是什么？比如说我讲，逻辑就是他后面的解释跟就是逻辑跟 true false 没有差的哦，不一样东西哦。他觉得 logical 一定要对啊。
我去参加 Integrable 课。
OK， 好。
这样签到你大家可以帮我签吗？因为我
可以，因为全部人也签不到。
还有这个礼拜的 quiz 是 lecture 几到几
啊？differentiability 的东西，
整个 OK。
好，你去找，OK，可以。觉得你我这3个是起点 OK， 没有问题。逻辑就是那个3段论嘛，你们出名的嘛，不是3段论呀？你只要 P implies Q， 有 P 就有 Q 了，就这样吧。就这样。他只是讲了，如果有爱的话，连
我5个人 at least，这个是什么讲？
就这样办了，
这个怎么讲？
就这样办了，就这样办了。
是有逻辑啊，我就讲他最丑。
要不要录一下他自己讲的话？
老师，你先我这个。
对对对，等下回去 play 一下你自己讲的话。你讲有逻辑就这个，然后这样子讲又有逻辑吗？
如果你讲话没有逻辑来分析的话，我自己讲的话有逻辑错的。
有逻辑来分析跟有逻辑不一样。OK， 好，非常好，非常好，非常好，非常好，非常好。有逻辑跟有用逻辑来解释是不一样。OK， 很好。very good， 是你讲啊。哦，我用你的话来解释啊。我不是讽刺你，我是用你的话来讲给你听吧。我没有讽刺你。Yeah， 你可以 replay 那个 recording 是你自己讲出来的。Yeah， 如果你觉得我一直在讽刺你的话，我就在讽刺你算了啦，随便，随便。你要这样子理解就随便，随便，Yeah， 随便 ，It's OK，doesn't matter。我不会乱讽刺人，我就这样吧。这是我的 attitude。很多人像你这样的也是 ，in particular KL 人呢，其实是南澳人，真的我没有骗你，真的我没有骗你，比你大人大很大人，好好跟他讲我讽刺他，硬少他，哇，听了随便他讲做是他的事情，他有天谴是他的事情，他踩到那个天谴是他的事情，我不会随便引烧人，我老实讲。啊，没有讽刺啊，我好好讲。喷啊，没有啦，也没有喷啊，就是好好讲吧啊，不要听就不要听啊，就这样吧。我是看很开啊，现在以前的话可能还会跟他 argue 一下，现在随便。就这样，没有啦，没有什么啊，就没有什么，就门关起来，冷气走就 OK。你看。如果讲到这样就讽刺的话，我们就讨论不下去哦。如果要讨论就好好讨论哦。如果你不要听我，我也不要听你，那就随便咯。不用讲了，反正那个人也是这样。他讲我不要跟你讲，他更聪明哦，他直接不要跟你讲这样，不是我不要跟他讲这样。可能我还给薄一点呢，某个人就这样吧。随便咯，他要做他自己的做法哦，随便他。他开心就好。不是你啊，希望不是你啊，希望不是你，反正有一个人这样，就希望不是你。又讽刺啊，不要紧，也不是洗年啊，就一个很大的人，算洗年吗？超级洗年 ，maybe。我洗年，我洗年吧 ，baby。所希望你不是这样的人啊，因为你还小嘛。如果你这样小就这样的话就，除非你做的东西很对啊，不然的话就，我不是讽刺你啊，我是来警告你 ，sorry。就是讲不听啊，就是讲一半，忽然间有情绪勒索啊，情绪这样子就。额外的东西跑进来，明明我们在讨论一个很逻辑的东西，然后忽然间你觉得我在引导你啊，情绪勒索我啊，然后各种的道德绑架啊什么的 ，why？ 明明我们是讨论 point 嘛，你不是很 logic 吗？忽然间问你，忽然间情绪勒索我，忽然间你讲我曲解你啊，讲我什么曲解你是你讲的，我没有讽刺你，我现在讲很明白，我没有在曲解人呢，我可以误解人，但是我不会曲解人，有些人是会曲解的，你知道什么叫曲解吗？就故意误解你。明明我在讲这东西，你就是懂了，你还要讲我讲了其他东西。我跟你讲啊，你这样做啊，你不要以为别人不懂哦，天会知道的啊。举头三尺有神明，你慢一点，你慢一点。啊什么？姓习的人啊，不姓习哦，你不姓习可以，你不要信，我就让你不要信。毛泽东死前都信我跟你讲。毛泽东叫全中国不要信神，他死前都信神。我跟你讲，你死了你就知道那一刻有没有神的存在。不要紧 ，OK， 没事，不要紧，你可以 try， 你可以 try， 你就不信嘛。 有些人很硬的嘛，有些人硬，我其实我也是很硬的，我其实很硬。有一首歌嘛，不是有歌吗？有一个歌叫什么“不撞南墙”呢？回头有听过吗？没有听过啊？下次 play 给你们听，很好听啊，这首歌啊。那个呀，不撞南墙。Okay, continue. So let's prove that fx equal to x is integrable, and then show that the integral from a to b is b squared minus a squared over 2. I mean, there are two kind of notation we learn, right? So we can write like this. Yeah, 上个礼拜. Yeah, we can write this as well. Because if you notice the definition of our integrability, right, we don't really care about the x's, actually. But then we care about the domain, and then we partition the domain. Does this match up with your calculus 1 calculation? Integrate x is x squared over 2, right? And then you take b squared. 对 forget yeah 对 yeah 加 c 加 c 哦 yeah 是 yeah 是 yeah 加 c 对，为什么有加 c 对，没有错，对。But then let's say if you have the 那个 c 啦 but then 你 take the difference 那个 c 不见了，对不对？Okay, so this left with b squared minus a squared over 2. Yeah, so that's why we didn't give you the idea of anti-derivative yet. Yeah. 只是我 try to link to 你学过的东西 but then 我们不会用那个东西我们不会用它，只是告诉你我们现在做的东西跟你以前做的东西是有关系的。Okay, so to prove integrability, right? So what do you use here? Okay, so we will try to produce a sequence of partitions such that the limit of LFPN is the same as the limit of UFPN. And these two is the same. Okay, so we'll create some PN and then show you that these two have the same limit. Okay. Well, the sequence we are testing here is not very weird one. It's the one you see from your Riemann sum, I guess. It's just equally partitioned. Equally spaced partition, so meaning you have sub-interval with the same length. Okay, so you take the original length, again divide by n, and then you add by a unit of your 1 over n length. This is what it is. Then let Pn be an equally spaced partition with n sub-interval. Okay, so if you draw this graph out, right? So if you draw this graph, and let's say A to B, that's why you divide into 1 over n. Okay. Okay, so then we need to compute what is LF piano and then UF piano. So since F is increasing, what do we have? We have that the sup of fx x in tk minus 1 to tk, okay, is equals to ftk. Right, this is because it's increasing, so meaning the supremum point will happen at the right end point. So we apply f of tk, and then infimum will happen on the left end point. Okay. So the first one, you get a plus k over n times b minus a. And then the other one, you get a plus k minus 1 over n times b minus a. Okay. So because our function is fx equal to x, right? So you just really get your left end and right end point as your height. Okay. And then what do we do? So therefore, we compute our f, which is equal to sum k equals to 1 to n of infimum fx of x in tk minus 1 to tk. Okay, time tk minus t. Okay, then you sub your inf into this calculation. So which is a plus this difference here. So this difference here, do you know what's this difference here? What's the difference here? Yeah, it's just b minus a over n, right? If you write down the left hand point, right hand point, you also get this. And you take a difference. But then it's just b minus a over n, because this is how you add up this. Right? Oh, sorry, this is not 1 over n, right? So this should be b minus a over 1 over n. Okay, because usually we put 0 to 1, so we will regard this as a whole length, but then in general, it's b minus a over. Okay, then how to compute this sum? This sum is a little bit tricky. So what should we do first? Maybe we can just put out b minus a. Is it possible? Yeah, and put out b minus a first. And then we can put those that are related to the sum into here. Okay, I mean for the first sum it's easy, right? You just add up a over n times, because there's nothing depending on k. So this one is just n times a over n. But then the other one is little bit involved. So what do you get if you sum k minus 1 from 1 to n? I forgot. Okay. I think this is the famous did by Gauss, right? Yeah, Gauss. Okay. So the formula is n minus 1 times n over 2. It used to be n plus 1 times n over 2, right? Then since we start with n minus 1, or we end with n minus 1. Okay, so if put all these things together, what do you get? You should get NA times NB. So together we get B minus A times B plus A equal 2 minus B minus A squared over 2. Okay, so do you know why I write it in this form here? Because later we're going to take limit of this thing n to infinity, right? And so you see that the second term actually disappear. Okay, so we're left with the first term. And actually the first term is what we want, right? B squared minus A squared over 2. Okay. The second disappear if we take n to infinity. Okay, how about U? How about UPN? UFPN for this one? Okay, so b minus a times a plus b minus a. Here we get that n times n plus 1 over 2n squared. Anyways. Okay, also you can see that the second term will disappear. Where you can see that the second term also disappear when n go to infinity. Okay. Yeah. So yeah. This is enough, right? Let's check the common limit criteria. Yeah. So I just check that this two limit is the same, and then it's integrable, and then that number is your integral. Okay. Good. 对，出这个偏有什么 trick 吗？I would say that's the first thing you could do. Okay, I think that's the first thing you could do. Okay. You might how to say because sometimes okay, because this function is actually quite regular. You get what I mean? It's like there's no weird thing happening here. Because maybe sometimes you could imagine maybe you have something like this, maybe. So then your partition, maybe you can focus on building here, right? I mean, like you can always make this into one of your endpoint. The point that maybe you think that could be a trouble, that's what I meant. Because this graph is regular, no matter how you cut, right? It should look relative the same for all the rectangle. Okay. But then imagine that this is your function to integrate, right? So if you cut your partition maybe like this, I would say why I draw this like this, maybe this could be I don't know, but it could be problematic. Okay, maybe I say some problematic point. Maybe you want to make these some problematic point into one of your endpoints, so that you can get your supremum or the infimum of your function properly. Okay, because otherwise sometimes this problematic point, right, could influence how you compute LFP and UFP. Then you can make your endpoint here actually. Yeah, instead of making like this, your partition, subpartition like that. Maybe this point could shoot out to infinity. This is what I mean, maybe. Yeah. But then this point, I think this function is it integrable? Maybe, yeah, it's unbounded. Yes, yes. But then you can imagine something like, oh, this one like this, and then this point is like quite high like that. Something like that. Does this affect your integrability or not? Yeah. Okay. If this is not, maybe I can add more. Does this affect or not? Okay. If countable, not. If I make it uncountably many, I think this one example we saw already, right? Yeah. If uncountable, then doesn't work. Maybe countable still work, but how to prove? Okay, so then this will affect how you build your partition already. The partition is countable, right? So you can make your subpartition mixing out these countable point. Okay. Does that make sense? Yeah. Yeah. Okay, so I think these are the point that you need to be careful where they affect you to compute the infimum or supremum. Okay. If let's see if we have different example. Yeah, I think we got one example, I think quite interesting one. Later we'll see. Right. Okay. So exercise, you can try and show another famous result, you know. Integral of 0, 1 of x squared should be equals to 1/3. Okay. Try to use the same technique. And because this function is also quite kind of regular, no singularity stuff. Right? You can use the equal partition method to find it. Yeah. Yeah. Just maybe the sum is a bit annoying. But then I recall that when I teach calculus 1, we also give them a lot of sum, like a table of sum for them. Yeah. Sum of like 1/n, sum of 1/n square, sum of 1/n cube, we give them the formula. Maybe those things you need to recall a little bit. Okay. 1, 1, 2, 7. Okay. Okay. So next, we're gonna prove that continuity will always imply integrability. Continuity implies integrability. Okay. So if f is continuous, then f is integrable. Okay, so very simple. Only two ideas here, continuity and integrability. So continuous and integrable. But then I think we slightly discussed here already, right? If it's continuous, what it means, on the continuous on the bounded set, you will have your extreme point, okay, extreme value theorem. Okay, you can hit your maximum and minimum. Okay. So let's write down those things. So we know that. So maybe first that continuous function on a closed interval implies that f is bounded. Okay, so this is by extreme value theorem. Okay, so we want to show integrability, right? Okay, so what we do is we'll use the theorem that we established at the start of the class. So what do we want to show? For every epsilon greater than 0, there exists a partition P epsilon such that UF P epsilon minus LF P epsilon, which is less than epsilon. Okay, so we want to do this. So what to do here? So we need to find P epsilon. Huh? So we need to find P epsilon. So how do we find P epsilon here? Okay, what are our concern here? Okay, what are our concern here? Well, you should think of it. If I fix this P epsilon, right, then it will fix how I find the sup or inf, because the sup and inf is defined across the sub-interval, okay, that you define. Okay, so meaning when you define this partition, right, you need to make sure your sup and inf make sense, okay, as close as with each other. Okay, so to do that, okay, so first thing we will do is we could control the image of F. Okay, so how do we control? So since F is continuous on the closed interval AB, right? F is uniformly continuous. Okay, so why do we need uniform continuity here? Maybe we recall the definition. So uniform continuity says what? If you fix epsilon, you will have a delta that works for all xy. Okay, that fall within the delta. Okay, so there will exist a delta. Okay, let's say I fix this epsilon to be b minus a. Okay, such that if your x and y fall into the range of delta epsilon b minus a here, then I can make sure their image is just within epsilon over b minus a. Okay. Okay. Maybe you might wonder why I want to keep it epsilon over b minus a. So maybe you want to guess later I'm gonna build b minus a to multiply with this guy so that I get epsilon. Okay. So later you should see something like that. You should expect something like that. Okay. So this epsilon game, right, you can think of it as if I'm gonna forecast to you what I'm gonna estimate. Okay? Like if epsilon over 2, maybe there are two things I need to combine, right? Okay, so okay. So the next part is to fix partition. Okay, so now we are going to fix our partition. So I will try to establish a partition that works. So what we're going to do is we're going to choose the length of your interval based on this n such that let me see, what's this delta? Okay, such that b minus a over n should be less than this delta of epsilon b minus a. Okay, does this make sense or not? Okay, so I have a function. I have a function. Okay, as long as this x and y is lie within delta of epsilon b minus a, then I have this height here controlled by epsilon over b minus a. And then now how do I pick this partition? I want to pick this partition such that the length of this subinterval here should be less than this delta. Okay, should be covered by this delta. Okay or not? Does it make sense? Okay, my partition will make this small. Okay, how small is it? Smaller than delta. And then we will let this p epsilon to be s naught x1 up to xn. Okay, because we got n part, right? Okay, we got n part of them. Okay, so now we try to compute our difference between sup and inf. Okay, difference between sup and inf. So we claim that. So now we claim. So we claim that the sup of f, okay, fx, minus the inf of fx, okay, such that x is in xi minus 1, xi, x is in xi minus y, xi, okay, which is less than epsilon over b minus a. Right, this is our claim. For I. But then we are guaranteed that this sup and inf exists, right? Because by extreme value theorem, okay, it exists. It is equal to some f x max and then equals to sum f x min. Okay, it's realized by some value because extreme value theorem says you must attain your maximum and minimum. If there's some function that attain this. But then did you remember what's the distance between this x max and x min here? You remember? What's the distance between these two? These two are coming from the same interval, right? Xi minus 1 minus xi. But then how we pick this interval? We make sure that it is less than, the largest length you can get is xi minus 1, right? But then this, I make sure that it is less than delta of epsilon of b minus a. But then when we say that 2 points is within this distance, we could make sure that their fx and fy is within b, is within epsilon over b minus a. Make sense? Okay. So this implies that this two number here is less than epsilon over b minus a. Okay, the difference between these two. Make sense? Okay, so by uniform continuity, the claim is true. The claim is true. Okay, good. Any question? Okay. 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 So then what do we need to do? In the end, we need to show for P epsilon. So we need to get this calculation. Yeah, I need to get this calculation done. So what's this calculation here? Can I replace my soup with mi? Is it okay? Replace with some other notation that look easier to write. Okay, so this is the soup. This is the inter. They are achievable because we are continuous function by extreme value theorem. This is achievable. Okay, and then what is this? This is just sum of mi minus mi. So big mi minus small mi times the difference of your sum. But then what is this? Just now we proved that this big mi minus small mi here is epsilon over b minus a. Okay, times xi. Then what is this? This is just a constant, right? Epsilon over b minus a. Then you just sum up all your subinterval, but then if you sum up all your subinterval, what do you get? You get the whole interval. I mean, sum up all the difference of your endpoint, your subinterval, what you get is epsilon over b minus a times b minus a, which is epsilon. Okay, done. Good. Good. Okay. Okay. Okay, very cool. So we can finish the one last thing. Okay, I think we are on schedule. Well, I like you class very much, actually. Every time I estimate where I'm gonna finish, I definitely finish there. Very good, very good. 啊？是因为我准了啊，不是你厉害。我不要相信你变厉害。OK， 没事，我们大家都在进步，是不是？是不是这样讲？对不对？对，我们大家都在进步。Okay, so next, last example we want to talk about here. We got 10 minutes. So integrable function can be discontinuous. So this example maybe show you a different way to pick partition. Maybe it's not the usual way you could think about how you take partition. Okay, so maybe this give you another idea how you're gonna take partition. So we could just look at this. I think this is Kronecker delta function. Okay, so if x is not 0, we just take 0. If x is 0, we just take 1. Okay, it's a bit like your heartbeat. Not like heartbeat. Is it like heartbeat? I mean like periodically. Okay, on this thing. Whether it's periodic or aperiodic depends on whether you are healthy or not. Okay, so something like this. The other place is 0. And then f is integrable on any closed bounded interval. Okay. And what's this integral? What do you think? What's the integral? What number should take? Positive, negative, 0. What's the area under this graph? 0. You think it's 0? There's a line there. Oh. Yeah. Okay. You see this more clearly in measure theory. Okay. So here only got one line. So line doesn't contribute to the area. But then if you got a lot of line, then it's an area. How many line? Okay. Yeah. I think you'll learn that more in measure theory. If you're gonna take is analysis 2. Hey, no. Here, what do we call it? Reanalysis, sorry. Reanalysis. Yeah. It's another ME course. Okay. Well, so what should we do here? So if you notice, right, this closed bounded interval, I didn't specify where, or I didn't specify where. If it is anywhere that doesn't contain 0, the point 0, right, it's very obvious that the integral is 0. Okay, because the sup and inf are just 0. Okay. But then the problematic integral is somewhere around here. This is the problematic part because the sup and inf is not the same. But you can think that this sup I can never reduce it. As long as I get 0, I can never reduce the sup. But then how is it possible that I can make the sup, I mean the sum of the sup and sum of the inf the same? Okay, so there's another room to play, which is the partition. Okay, you're gonna play with this partition here. Okay, although you cannot reduce the height, but then you can reduce the width. Okay, so let's see. So if 0 is not in closed interval AB here, then f is actually easily integrable. Okay. Because UF and LF is always the same, which is 0. Okay, so now assume that our integral involves the point 0. Okay, then we could again use the epsilon, P epsilon definition of integrability. Yeah, so maybe let's draw a picture to help you. Okay, let's draw a picture. So let's say the point AB is here. Okay, and then you got this problematic point here. Okay, so how do you build your partition? What partition you should consider here? Okay, we want to create a partition such that UFP epsilon minus LFP epsilon is less than epsilon always. Okay, so you should think of UFP and LFP. What are the terms inside there? Okay, UFP there's a sup, right? And then LFP there's an inf. Okay, so you can think of the inf, right? no matter how you fix your partition, right, you should always get a point as 0, right? So your LFP is always 0. So meaning if you want to make your UFP and LFP to be the same, right, you need to make sure your UFP is always as close to 0 as possible. Okay, you want to make your UFP as close to 0 as possible. Okay, but then what's the definition of UFP? The sup times the length of your subinterval. Okay, the sup times your length of your subinterval. But then the sup is always 1, no? If you contain 0 there. So is it possible to make your length of subinterval as close to epsilon as possible, as 0 as possible? So that means what? You need to make your width or the length of your subinterval depending on your epsilon. Okay, you need to make it depending on the epsilon. So one way to do that is you can pick, for example, minus epsilon over 3 to epsilon over 3. Okay, maybe you want to think why I picked 3 lah. Later I'll show you why I picked 3. So then what we choose here? We choose P epsilon to be A minus epsilon over 3, and then B. Okay. So I didn't create more points inside my partition. What I do is I consider the partition with the length decreasing when it involves the point 0. Okay, get smaller and smaller and smaller. Okay, look, let's see why this works. So if you compute UFP epsilon, right, what do you get? You get 0 times minus epsilon over 3 minus A plus 1 times epsilon over 3 plus epsilon over 3 plus 0 times B minus epsilon over 3. Okay, so altogether, what do I get? I get 2 epsilon over 3. Okay, just from the width of your interval, 2 epsilon over 3. LFP epsilon, this is just 0 times 0 times something times 0 times something, which is 0. Okay, 3 parts. Okay, both 3 parts here will contain some point that have 0. Okay, so the infimum is 0. Make sense? Okay, then so we compute the difference between UFP epsilon and LFP epsilon. Okay, so all together, what do we get? We get 2 epsilon over 3 minus 0, which is 2 epsilon over 3, which is less than epsilon. Okay, so we found a P epsilon for all epsilon such that the difference of UFP epsilon minus LFP epsilon is less than epsilon. Okay, so hence F is integrable. Okay, so hence F is integrable. Moreover, this integral here should be equals to UF and LF. Okay, so UF is what? LF is what? So LF is the supremum of the set containing 0, right, which is 0. But then UF is the inf, okay, inf of set of number 2 epsilon over 3. What's the inf of this? Okay, so the inf of this should be 0. Okay, so in both cases you get 0. Okay, are we done yet? Have we considered all the cases yet? If we're not done yet, then what are the cases we miss? Huh? 0? What do you mean? Oh, yeah, right. So we consider 0 is in between A and B, right? So what if one of them is 0? Okay, so meaning your interval like start from 0 to something greater, positive, or something negative. Okay, so what do you think? If 0 is your endpoint of your operation domain, what picture can you draw here? Ah, 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 ah，它有个能 equal， but then 这个图这个图 look a bit different already 哦。Because when it is equal, you need to push your A to here, right? So you need to start here. Okay. But still works. Okay, so you just make your one-sided. The first partition here get very close to A. No? Yeah, I think epsilon over 2 will works already. You want to use epsilon over 3 also can, huh? 下面这样子做什么？ I mean, what you do here is pretty fixed after you fix your partition. So the point here is if your A is equal to 0, so how do you fix your partition? Once you fix your partition, your L and U is already fixed already because it's a formula. It's depending on your partition. Yeah. A equals B equals 0, 你讲。So I mean, the point here is to fix your partition before you calculate your U and L. Okay. So when A equals to 0, so meaning what? So this A here get pushed to 0, right? Okay. So also this part here will disappear. You don't need to care about already. Okay. So let me draw you the picture. Just start from 0 to some B, right? Then your partition should look something like this. Okay. Yeah. So you can see that this partition, when epsilon get very small, right, it will get very close to 0. Okay. 问题吗？问题。Then once you fix this partition, U and L is already fixed already. This is the formula, depending on your partition. Okay, yeah. 你改不了了这个 U 跟 F， 它已经是个 formula 来了，一定是 sub 乘它的那个 length 那个 difference。Okay, but then the thing you can change is this partition. 你要选择什么 partition? Okay, such that 你的 sub 跟 im 是 make sense， 可以 compute 到你要的东西。OK 吗？ Okay, so we have covered all the cases. If B is 0, right, then it's similar. 你就去 minus epsilon over 2, then 就可以 work. OK, 你不要 epsilon over 2也是可以的，你只要选一个东西小于 epsilon 就好。I mean, after you compute you get something smaller than epsilon, then you are good already. OK, 没问题吗？没问题。Right, so this function is integrable and then integrate 0. Okay, no question? No question? Okay, if no question, maybe 你觉得我们要继续 quiz 还是我们可以暂停 quiz？ 暂停 quiz？ 啊？对，我们可以选择 cut 掉 quiz。But then 分数我们就停在第几个，我们就你要赚多点分。不是，我的意思是说，可能有5分 allocate to quiz 嘛，对不对？如果我们只做5个 quiz， 我们就出150咯；如果出6个 quiz， 我们就出160咯。
你要想也有可能。是因为我这是如果是你拿4分的话，还是你拿？我没当过后，我必要一点所以有一点机会没有看到。我觉得啦，我 estimate。
好，我们明天投票要不要？
可以，
因为我好像 list 在里面。对，5分 啊，sorry，拜神，sorry，拜神啊，
还是存不了。
对，好像是，如果没有记错啊。然后什么叫 OK 还是不 OK？
我是想要不 OK 啦，你刚
quiz 一个东西是分数啦，另外一个东西就是督促你们做 revision 罢了，或者还有一个 testing 是 test 一下你们懂的东西跟我懂的东西是不是一样。对，
哎，
不会，只是说多余的时间，我希望你们去花去做你们 project，这个意思了。因为你还有一个 project 要讲嘛，对不对？但那些时间你就拿去做你的 project，对吧？make sense 吗？想一下。也是这样讲吗？也是这样讲吗？可以吗？想一下，因为好像我 list 有5个是吗？quiz，如果 list 在那个 course info 里面，如果没有错的话，好像只有 list 5个吧。因为我剩下时间是希望你们拿去做那个 project 啊，如果你愿意，我是 OK 的。你们努力，我是可以陪你们努力的。我最怕学生不努力，我最怕学生不学习嘛。如果你们很愿意学习，我陪你们。反正赚到是你们啊，不是我啊，是不是？你会是你啊，那也是我。你会啊，你赚了钱，你会请我吃饭吗？
可能会
啊，可能会啊，这样 OK。evaluation，我们这个坎过不去啊，炮太骄傲，不要紧，我还是。